Hello everyone and welcome back to Diksha Karnataka YouTube channel. Currently you are watching KCET 60 out of 60 in physics series, and very good news for you because we have created a separate playlist where you can check each and every video that we are doing in this channel, and every day we are going live at 9 p.m. with a new video every day. Okay, 9 p.m. Mark your calendar, mark your time. Every day 9 p.m. there will be a physics video, and also we will publish what all going to come in our channel every day in our website. The link will be given in the description below. Also, we are going to give you one lecture from Monday till Saturday, every day one lecture, and on Sunday there will be a test. As I said, KCET Premier League, every Sunday there will be a test at 10 a.m. You will be given a question paper, set of 30 questions that you have the entire day to answer, and at 8 p.m. on Sunday we are going to give you the solution in a detailed video format. You can go and you can check all the answers. Now in this series we are discussing concepts from chapters. We are discussing PYQs. There will be a separate PYQ included in our daily lecture. So suppose I have completed this chapter today, then tomorrow or maybe day after tomorrow there will be a PYQ based on this chapter as well. So don't worry, we have you covered in all the aspects. You don't need to go anywhere, just you need to click on the description below on the link and join our WhatsApp channel. There everything will be provided to you, including the notes that we are discussing in the class, the homework, etc. Also the question paper on Sunday will be available on our WhatsApp channel. So don't forget to join our WhatsApp channel. And if you are watching this video for the first time, then don't forget to click on the subscribe button in the given below and join our cause. Now let's start with KCET 2025's lecture series video number 2. Today we are going to discuss electric charges and field part 2. We have already completed part 1. In part 1 we have covered electric charges, we have covered Coulomb's law, we have covered electric fields and electric field lines. Today we will start with electric dipole, then slowly we will move towards Gauss's law. Also in between our video we will also give you the solution that I asked you to answer in our previous video. Most of you have not answered. Many of you, I know many of you have seen that video, but I hope that you have not wasting your time. You should try and answer those questions and mention the answer in the comment below. During this lecture, sometime in the middle, we will solve yesterday's video, yesterday's questions. Also, after that lecture today, we will give you 2 more homework to solve. And if you are studying for KCET 2025, I hope you will go through the entire lecture and try to answer those 2 questions and mention the answer in the comment below. Now, let's start with today's lecture. What all we are going to cover in today's lecture? First, we will cover electric dipole. Next, we will cover electric dipole moment. Then we will cover electric field due to a dipole. Then we will discuss about electric dipole in an electric field. Next, we will discuss about electric flux. Then we will discuss about charge distribution. There are 3 different types of charge distribution. Then we will discuss Gauss's law, and last we will discuss applications of Gauss's law. So let's start with electric dipole. What is the meaning of electric? Electric means obviously charges, electrons, they are called anything related to that is called electric. And dipole. Okay, pole means what? Pole means in normal English, pole means a point. Okay, or you can say a rod. And dipole, di means 2. So 2 charges connected by a rod or connected by something that is we are considering them as dipole. Okay, or 2 points, 2 point charges connected by invisible rod is called a dipole. So 2 equal and opposite charges. Now let's discuss more technical aspect about it. The actual definition of dipole. two equal and opposite charges separated by a small distance. Okay, so two equal and opposite charges separated by a small distance is known as electric dipole. Okay, so two equal and opposite charges, that means they has to be equal. Okay, so if this is say 10 coulomb, other one will be minus 10 coulomb. Okay, equal, opposite, separated by small distance. The distance should be very small. So you need to remember that they are equal, they are opposite, that is their sign is opposite, and the distance between them is small. These three things you must remember. Okay, what all? So here we have given you the basic diagram of dipole that is given in your books. So we have one charge plus q, another charge minus q. Okay, so if one charge is plus q, the other one has to be minus q. Otherwise we cannot call it as a dipole. We will not consider it as a dipole. Now distance between them, generally we represent the distance between these two charges by 2a. So what is the meaning of 2a? Basically 2a means we divide this distance in two parts. One is this a, another a. Why so? Because that reduces our mathematics. This only thing that it helps is it reduces our mathematical calculations, nothing else. Okay, if someone comes tomorrow and say, okay, I will use the symbol d for the distance, that is also fine. But if when you are going to do some mathematics, if you are using d instead of 2a, then maybe it will be little bit complicated. Someone might say, okay, instead of 2a I will only use a. That is also fine, but this final mathematical calculation, final mathematical detail will be little bit complicated. That's it. Only thing to consider this 2a is to reduce the mathematical load. Otherwise you can consider any other variable, does not matter. Distance is distance. In some cases we will directly use the distance, some cases we will divide it by 2. So suppose the distance is given 10 centimeter. You need to remember that the distance between two dipoles suppose is given 10 centimeter, for example. Then you need to remember that 2a itself is 10 centimeter, not a. Okay, so you don't need to multiply it with 2. That is the basic thing I ask you to remember. Okay, whenever the distance is given, the entire 2a is given as it is. Okay, so now when you are applying it to some formula, suppose in that formula a is used, then what you have to do, you have to divide it by 2 to get 5. Okay, but otherwise in most cases you will use 10 centimeter as it is without changing. Now next, suppose we have a HCl molecule. So let us understand the real example of a dipole. So in HCl what happens, we know that hydrogen gives one electron, chlorine gives one electron, and they form a covalent bond, and then these electrons normally, not in hydrogen HCl liquid, HCl in water, HCl gas. Okay, in HCl gas this electron pair is shared among hydrogen and chlorine. So now it has 8 electrons in his outer shell. Hydrogen has 2 electrons in his outer shell, so both are stable. Now because of higher electron affinity, what happens, this electron pair tends to move towards the chlorine, right? We know already everything that due to higher electron affinity, these things tend to move near chlorine, right? So this electron pair goes closely to the chlorine. Okay, so hydrogen give one electron, chlorine give one electron, then chlorine say, okay, we already shared everything, now give me those 2 electrons, I want to keep it near me. Okay, so so this chlorine is being kept near this chlorine. Now this becomes slightly negatively charged because this electron pair is close to chlorine, right? Chlorine generally had only one electron, he shared only one electron, but now he take care of hydrogen's electron as well. So that's why now it becomes slightly negative and hydrogen becomes slightly positive because it gave away its electron and now it is slightly positive, right? So this thing, and their separation is very small because they are only molecular length, right? In molecular length it may be nanometer, so their distance is very small. So that's why we can say this is an ideal example of dipole. So any molecules, any uh, bonds, wherever there is it is a bonds where electron pair is being exchanged, we can consider them as dipole. Okay, in some cases if electron is exactly at the middle, then we cannot consider them as dipole, but otherwise if there is a ionic exchange of electron is happening, we can consider them as dipole. Okay, now let's move on. Let us now discuss about dipole moment. Electric dipole moment is the product of magnitude of one of the charges and the distance between them. So it is the product. Product means multiplication, right? Magnitude of one of the charges, magnitude of one of the charges and the distance between them. Okay, so we have seen that two dipoles, we consider two dipoles plus q and minus q, and we said the distance between them is 2a. Then the dipole moment is given by P equals to q times 2a n cap. Now dipole moment is a vector quantity, you need to remember that dipole moment is a vector quantity. So that's why we have used this vector symbol. And if you remember this q charge was a scalar quantity, and the distance we are not sure which direction we want to consider this distance, and we have used a unit vector n cap to denote the direction. Now what is the direction of this dipole moment? Remember that the dipole moment is always from negative to positive, negative to positive, you have to remember that. Okay, dipole moment, the direction of dipole moment is always from negative to positive. So this is the direction of dipole moment. Okay, now n is the unit vector from negative to positive charge. Okay, now thus the direction of dipole moment is from negative to positive charge. So dipole moment always points from negative to positive. Okay, exactly opposite to the field line. If you remember, field lines starts at positive, ends at negative, whereas dipole moment points from negative to positive. Okay, this is just a simple thing that you need to remember, that for dipole moment is exactly opposite to that of electric field. Now for points on the axis, suppose we have a dipole, okay, and this distance is a, this distance is also a, as I said. So we divide it into two halves, and we are inspecting electric field at a distance r from the center. Okay, the distance will always be measured from the center, because if I measure it from positive charge, the negative charge will say, why you are measuring from positive charge, what mistakes I have done. If you are measuring from negative charge, positive charge will say, what mistakes I have done. So no one has any mistakes, so what we will do, we will measure it from the center, so that everyone is happy. Now if you are measuring from the center, then this a plus a is very handy, and if you know the derivation, we are going to do the derivation as well in another series. There you will see how we are doing the derivation. Now if you do the derivation, you know that electric field is given by EA equals to 1 by 4 pi epsilon naught 2p by r cube. Now you don't need to cancel this, because this is a constant, it comes everywhere, and I say this is a tika, this is like a tika before going to a temple. So or wherever you are going, this is like a topi. Okay, so this is the constant, it will always come, and if you write in terms of vector, then it will be like this. Okay, so EA and is equal to EA vector, that is on the axis, we are saying the electric field at this point is EA, and so this electric field will be equals to 1 by 4 pi epsilon naught 2p vector divided by r cube. Now p vector, as I already mentioned, is charge times total distance n cap. N cap is from negative to positive. Okay, so this is the formula for electric field on the axis of a dipole. You remember that. Now, on the equatorial plane means if you take the distance between the dipole and if you bisect it, okay, and then if you consider an imaginary plane in that bisector, okay, on each and every point, this is valid. So that's why it is called equatorial plane. And if you are trying to find the electric field here, okay, equatorial plane, we say EP, okay, and vectorially it will be vector in this direction, it will be in this direction. So there is a negative sign. Negative sign indicates that electric field is from positive to negative, that is electric field is in this direction, okay, electric field is in this direction, whereas dipole moment is in this direction, negative to positive. So that's why there is a negative sign. Magnitude wise you can say electric on the axis of the dipole, the electric field is twice that of on the equatorial plane, right? If you remember last formula, we have seen that E axis is equals to 1 by 4 pi epsilon naught 2p by r cube, and this formula we are seeing that electric field is only p by r cube, right? So equatorial plane is basically half of that of on the axis. So on the axis it is twice that of equatorial plane. So on the axis it is more, on the equatorial plane it is slightly less for same distance. Okay, for same distance, if you consider the same distance r or a same distance r here, in both cases you can say axis is twice as strong as equatorial plane. Okay, so this formula is important. Sometimes they will ask you objective question based on this, and especially for PU board, they ask if the equatorial on the distance r, if electric field is EA on the axis and ER on the equatorial plane, then which of the following relationship is correct. Okay, so they might ask you that question in your PU board as well in MCQ. Also, you need to remember this, that in both cases, in equatorial plane as well as in axis, the electric field varies with 1 by r cube. So far, whatever we have done for a point object, and you will do, we will see in our future as well, most cases we will see electric field is actually dependent on 1 by r square, right? For normal point charge, electric field is 1 by r square, but for a dipole, be it on the axis, be it on the equatorial plane, E is always proportional to 1 by r cube. Okay, so dipole is, it is always 1 by r cube. For point charge, it is 1 by r square. 1 year this question came. Okay, so don't ignore this as well. You have to pay attention to the details. Now let's move on. Now next is dipole in an uniform external field. So we have an uniform external field. Uniform external field means all the lines are parallel and electric field is constant, and you have a dipole at some angle theta. Okay, so the dipole is at an angle theta, so dipole is moment is from negative to positive, right? So dipole moment is negative to positive, and this angle is theta. Okay, if this angle is theta, okay, so dipole is rotated such that the dipole moment is in this direction, electric field is in this direction, the angle between electric field and dipole is theta. Then the torque. So first let us understand what will happen. This negative charge will tend to move in the opposite direction of the electric field, whereas the positive charge will tend to move in the direction of electric field, and they will experience a rotational force. We call that rotational force as torque, right? So whenever there is an equal and opposite force acting on an object but separated by a distance, we call it as torque, right? So this torque will tend to rotate this dipole, and that torque is given by P cross E, vector product of P and E in scalar form. Most of the cases you will be asked to solve using scalar form, but you should know the vector form as well. Sometimes if the question paper level is slightly difficult, they might ask you to do a cross product as well, but the cross product will not be very difficult because they will reduce the terms and all, so that we will see later on. But you should remember this cross product formula as well, and the scalar form as well. Torque is equal to PE sine theta. It is sine theta because it is cross product. We know that cross product means sine, dot product means cos, right? That you need to remember that since it is a cross product, the final result will be sine theta and not cos theta. Okay, so PE sine theta. Many students get confused between sine and cos. That's why I mentioned it here that this is a cross product and not a dot product. If cross product is there, that means it is PE sine theta. Okay. Now let's look into a problem. An electric dipole with a dipole moment 4 times 10 to the power of minus 9 coulomb meter. So one thing that you need to remember, the unit of dipole moment is coulomb meter. Okay. Now dipole moment itself is given. That means P is given. Okay, 4 times 10 to the power of minus 9. Okay, is aligned at 30 degrees. So theta is given. Aligned at 30 degrees with the direction of uniform electric field of magnitude. So electric field of magnitude is also given 5 times 10 to the power of 4 Newton per coulomb, right? The magnitude of the torque acting on the dipole, and this is very latest, 2022 it came. Okay, so the magnitude of torque they have asked you to find. The torque is PE what, sine or cos? Sine theta, right? So PE sine theta, P is 4 times 10 to the power of minus 9, E is 5 times 10 to the power of 4, sine theta, sine 30. Now what is sine 30? Do you remember? 4 5s are 20 times 10 to the power of minus 9 plus 4 minus 5, right? I told you they are added. Now sine 30 is what? Half. Okay, if you forget how to remember these values, it is done in our basic mathematics video. You can go and check how you can remember all the angles, and you can calculate it yourself. That is done in that channel, in that video. So don't miss that if you are wondering how to calculate. Now 10 times 10 to the power of minus 5. So it is 10 to the power 1 times 10 to the power of minus 5, right? So it will become 10 to the power of minus 4. Okay, so 10 to the power of minus 4 is this. So this is the correct answer. Okay, so it is not difficult. Any problem that you are trying to solve is fundamentally not difficult in KCET. Sometimes they give you a longer calculations. Okay, this is neither longer calculation, this is neither fundamentally difficult. Okay, so don't worry about KCET 2025 exam. If you are preparing for it, it will be smooth as butter if you are learning with us. Now it is time for me to give you the answer for yesterday's lecture. We have solved, we have given two homework questions. So let us solve. 2 point charges plus 1 microcoulomb. Okay, so 2 point charges plus 1 microcoulomb, 0.1 microcoulomb. Another charge 0.1 microcoulomb. Both are equal in magnitude. Okay, each are separated by a distance 0.2 meter in air. So they are separated by a distance. Okay, they are separated by a distance 0.2 meter in air. So the distance between them is 0.2 meter. Now what is the question? Question is the electric field strength at the midpoint between them. So they have asked you to find the electric field strength at the midpoint, right? Now this is a very simple problem. Okay, if you use your brain, you don't need to look into anything. You just simply answer this question, and I didn't get a single answer for that in our last video, so it is very disappointing. If you are watching this video, don't forget to wait till the homework is given and answer those two homework. That is for your own benefit, and mention the answer in the comment below. Now, due to this positive charge, what is the electric field? Electric field, due to this positive charge, the electric field will be in this direction, right? Away from, right? Away from the charge, because both of them are positive. Now, due to this positive charge, electric field will be again away from in this side. And both of them are equidistant, right? We know that electric field is E equals to K Q by R square. Now, R is same for both of them. So, what will be the magnitude? magnitude will also be same. So for both the charges, magnitude will also be the same. So one will be on the right hand side, one will be on the left hand side. So they will cancel each other. In that case, we can say that the electric field strength is 0 at the midpoint between two equal charges. So electric field strength is 0 in the midpoint between two charges. This is very important concept. You should remember that. Now let's move on to the next question. 27 identical drops of liquid carrying equal charge coalesce to form a large drop. The electric field on the surface of the large drop is dash times on the surface of the drop. So what is the question? They have given you 27 small charges, 27 small charges, okay, like that, dot dot dot, okay. Each of them has equal amount of charge Q, okay, and they combine together. Coalesce means they fall on each other to form a large drop. So when the large drop is formed, okay, so here they have some electric field on the surface. Here they have some electric field on the surface, and they are, this is ES. And once the large drop is formed, what will be the ES now? ES dash on the surface, okay. What will be the new ES dash on the surface, that you have to calculate, okay. So for that, first of all, if such question comes, no matter which exam you are appearing for, JEE, NEET or any other exam, first thing you have to do, you have to compare the volume and then find the radius. Very, very important. Suppose the radius of the smaller drop was small r and radius of the larger drop is capital R, okay. Now one thing that is not changing is the volume, total volume of when you take 10 drops of water, okay. If you add them, the total volume remain unchanged, right? That is the property. So liquid is incompressible. If incompressible liquid is used, liquid is generally incompressible, and that's why the total volume should remain constant. So what is the volume of the smaller drop? Smaller drop means what? What is the shape? Shape of a drop is spherical. So spherical shape means what is the volume? So volume of a single drop, small drop, is 4/3 pi r cube, right? This is the volume of a sphere. Now this is the volume of a single drop. How many drops are there? 27, right? So this should be the volume of the larger drop, okay. So larger, it is not a drop, but it is still they are mentioning large drop. So this is the volume of the large drop. But if the radius of the large drop is capital R, then again we can write this volume as 4 pi capital R cube, right? This is from the small drop, because these all are combined together and they form the drop. So this is the small drop, total volume of the small drop. This is the volume of the large drop. They should equal. Now it's easy. You can cancel 4/3 pi. Pi cancels. Now what you get? You get R cube equals to 27 small r cube, right? Very common problem. So R should be equals to 3r, right? So the radius, the big radius should be equals to 3 times the radius of the small sphere, right? Now what we have to do, we have to compare the electric field. Now to compare the electric field, we are going to discuss this in a while, but you should remember that whenever we are comparing the electric field of a spherical object, okay, electric field on the surface, outside the surface or close to the surface, what we can do is we can consider this entire charge is located at the center of this, okay. We can consider this is located at the center, and whatever is the distance from the center, we can treat that as a point charge, right? So if you consider the entire charge Q is located at the center, okay, entire charge Q is located at the center, then what is the electric field on the surface? So electric field on the surface will be electric field due to a point charge. What is the electric field due to a point charge? Electric field due to a point charge is ES equals to K Q pi r square. I just wrote that in our previous case, right? Electric field is due to a point charge is E S K Q by r square. Now, similarly we can write the electric field for the bigger drop as well. So what we have to do, we have to consider entire charge on the sphere is concentrated at the center. Okay, entire charge on the sphere is concentrated on the center. Whatever distance is, that will be our r, and whatever total charge on the sphere, that will be our q. Okay, so only thing that you have to do is the consider individually. So es dash is k. What is the total charge on the sphere? How many spheres are there? 27 spheres are there. So total charge will be 27 q. Right? So total charge will be, this is for a single charge, single drop. This is for the entire drop when they coalesce into a single drop. Right? So 27 q is the total charge, and instead of r square, what we have to use? We have to use the capital R square. Right? So let me continue. Es dash is equals to k times 27q divided by r square. So what is the value of r? R we have already calculated, it is equals to 3r. So we have to put this value here. Okay, 3r square. So k 27q divided by 9r square. So 9, 27, it cancels, it becomes 3. So it will become 3kq by r square. So this is the new electric field on the surface. So this new electric field, what is this value? This value is nothing but Es. So we can write this as Es dash is equals to 3Es. Right? So this is the relation we were looking for. So the correct answer is this. So don't get fooled. Don't think that whenever we take 27 separate objects and coalesce them, it will be 27 times the electric field. No. Okay, this is a very common mistake students make. Many students answer this without properly solving this question. There is similar question available for electric potential as well. Once we complete the electric potential chapter, that will also be a problem. So you can try that. If you have solved the electric potential, you can try to answer that. What is the electric potential of a sphere if 27 spheres are coalesced into a single sphere? What is the electric potential on the surface? That is a bonus question. Okay, you should try. Let us consider we are watering our garden using a pipe. Okay, the opening of the pipe is delta S, and the velocity through which the water is coming out of the pipe is V. Okay, so V is the velocity. Okay, velocity of the water coming out of this pipe. Now, what is the volume of liquid coming out of this pipe in each second? So what is the value of velocity? What is the value of volume? Okay, what is the volume of liquid coming out of this pipe each second? So what you have to do? You have to take the area, you have to take the velocity, and then you have to multiply them, right? So that is the basically the volume. That will give you the volume of the liquid coming out of the pipe, right? So this volume is given called flux. This volume, whatever volume of liquid coming out of this pipe, that is called flux of that liquid. Okay, flux comes from this term. Okay, so volume of fluid coming out in 1 second is called flux. That is how flux is defined. Now for this case, we have already seen that this is equals to delta S times V, or V delta S. This is called the flux. And now what will happen? What will happen if the pipe is not perpendicular? The opening is cut slantingly, so that you can see the slant cut. Because of that, the volume, the velocity is no longer in the direction of flow. Okay, so velocity is in this direction, but this opening is pointing towards some other direction. Now what will be the flux in this case? Simple. In this case, what we have to do, we have to consider this angle theta. Okay, and you can find the flux taking cos theta. So basically this is coming out to be a dot product. We will explain it a little bit later once we define the surface area. surface unit vector. Okay, but for now you should remember that whenever there is an angle between the velocity and the surface area, it should be a cos theta. Now this is not the electric flux, this is normal flux. Okay, normal flux means when water is coming out. Okay, how much water we have to put in the garden, so that is the flux. Now when we are talking about electricity, okay, electric field, even though nothing is actually flowing, electric field is not flowing, it is changing, right? It is changing, it is increasing, it is decreasing, but you can consider it to be as if it is a flowing water. Okay, and as you moving ahead, the speed of the water is decreasing, right? So you can consider this as a flowing water. And if you consider a plane like this, okay, then if the plane is perpendicular to the direction of electric field, okay, the plane is perpendicular to the direction of electric field, in that case you can say the delta S, the direction of delta S is the same direction as electric field, and you can say the electric flux in this case is given by, the symbol for flux is phi. Okay, this is the symbol for flux and this is phi. Phi is equals to E delta S. Okay, phi is equals to E delta S. Now what will happen similarly if this plane is no longer perpendicular, but instead the delta S is pointing at some angle? In that case, again similarly we can write the electric flux as E delta S cos theta, or we can write this as E dot delta S. Now what is delta S? Delta S is called area vector. What is that? What is the area vector? Suppose we have a surface, whatever surface it may be, suppose we have a surface, okay, and the surface is kept it like this, okay, like this, the surface is kept like this. Then if we draw a perpendicular on the surface, that perpendicular represents the surface vector, surface area vector. This is also called normal to the surface. Okay, normal to the surface means this is the direction of the area vector. So if this is the surface, if you draw a normal like this, this is called the area vector. This is the direction of area vector. Now whenever we are having a surface, there can be a perpendicular in this direction, right? There can be a perpendicular in this direction also. So delta S may be in this case may be positive, in this case may be negative. Now which one to take, which one to consider? So for example, delta S can be in this case, delta S could be in this direction, or it could have been in this direction as well. In this case it could have been in this direction as well, but we are not considering this direction. We are not considering this direction. Why? Because you have to take it in the sense where the electric field is moving. So electric field is moving in this direction, so we will take the area vector in the same direction. Okay, if the electric field is moving in the opposite direction, we will take the area vector in that direction. Electric field in this case in this direction, so delta S will also be in this direction. Now electric field in this case is in this direction. Now this angle is acute angle, right? So this angle is acute angle means it is less than 90 degrees. So we will consider delta S in this direction and not where it will become an obtuse angle. Okay, so be careful about that. Now let us discuss about continuous charge distribution. So flask is done. We will use this concept of flask in very soon. Before going into that, let us discuss about continuous charge distribution. So far whatever we have studied, maybe it's superposition principle, maybe individual charges, we already said that there is only one single charge, and due to that we are finding the electric field. If we have two different charges, Q1, Q2, what we do? We find the electric field between individual charges, and then we apply superposition principle, and then we find the electric field. Now what if instead of having one or two charges, there are numerous charges, okay, and they are very close to each other? Okay, whenever we see such kind of thing, we call them as charge distribution. It can be random charge distribution, it can be uniform charge distribution. Random charge distribution means what? What is the meaning of random charge distribution? Suppose we have a surface, some area, some volume, okay, where the charge, one charge is located here, here, here. There are multiple charges, maybe 1,000 charges, but there is no pattern between them. Then this is called random charge distribution. Okay, or suppose number of charges in this region is very high, whereas number of charges in this region is very low. That is also called non-uniform or random charge distribution, also sometimes called non-uniform charge distribution. But if the charges are distributed evenly, then we call them as continuous or uniform charge distribution. Uniform, continuous, everything is fine. Uniform means charges are separated uniformly, distributed uniformly, and continuous means there is no break. In between there is no cut or hole. Okay, that's why we call it continuous charge distribution. Now, there are three types of charge distribution you need to remember. One is line charge distribution. Line charge means, as the name suggests, it's a single straight line. Okay, ideally infinite. Okay, and if you take any portion of it, each portion will have equal length. If you take the each portion of equal length, each portion will have equal amount of charge. Okay, so this is called line charge. So it has charge on this line. So this line is not uncharged. This is line. This has some charge on it, and it is uniform and continuous. Okay, so any portion if you take, it will have equal amount of charge from another equal portion from another distance. Okay, now how we treat these things? We treat these things by taking small portion of the wire, small portion of the line. Okay, and we say this charge we can treat them as discrete individual charges. Okay, suppose I want to find electric field here. That is what we are interested, right? To do that, what we will do, we will consider a small portion of it. Okay, and we will say this is like a point charge, this is like a discrete point charge, and then we will find the electric field due to this point charge. And then we will do integration. Okay, if we do integration, we will find the total electric field at that point. But we are not going into that detail. What we need to remember whenever we are talking about line charge is that the line charge density. Okay, that is very important. The fact I said, if you take any portion of the wire from anywhere, and you will see that they have equal amount of charge. So what we will do, we will take a unit length. Unit length means normally 1 meter. Suppose 1 meter. So unit length, if we take any unit length of wire, okay, whatever charge is in that unit length, we call that unit length as lambda. Okay, so lambda is the charge per unit length. That is the definition. Now, what will happen if I take any other length, say L? Okay, if I take any other length L, what will be the total charge in that length? Total charge in that length, capital Q, will be lambda times L. Right? So, for 1 meter length, charge is lambda. For L meter length, it will be L times lambda. Right? So, this is the charge. This way, you don't need to remember the exact charge on the line. Line is infinite. So, there will be infinite amount of charge. Right? So, you don't need to concentrate on what is the total charge on that line. Only thing you need to concentrate is the what is the charge density of that line. And what is the unit of this charge density? Very important for PU board exam. If you are going for PU board exam, what is the unit of line charge density? Unit of line charge, what is the lambda? Lambda is charge divided by length, right? So, what is the unit of charge? Charge unit is coulomb. What is the unit of length? Length unit is meter. So, coulomb per meter is the unit of line charge density that you need to remember. Similarly, instead of line, if we consider a surface, if we consider a very large surface having charge distributed on this. So, first was 2 dimension. This is first was 1 dimension. 1 dimension. This is 2 dimension, right? So, line is a 1 dimensional thing and a surface is 2 dimensional. Next, obviously, we will go to 3 dimension. Okay. So, suppose we have a surface with charges distributed among on it, and any portion if you take, they will have equal amount of charge. Similarly, what we will do, we will take 1 meter by 1 meter or unit area. We will not say 1 meter by 1 meter. We will, in our head, we know that this 1 meter by 1 meter, but it can be in any unit. Okay, it can be 1 centimeter by 1 centimeter as well, but unit will be only changing. But for simplicity, we will say unit area. So if you take 1 unit area, okay, the charge in that unit area is called sigma. Okay, lambda sigma. Sigma is the charge density, surface charge density is called surface charge density. Okay, now if I take any area, suppose I take any random area of area A. Okay, then what is the charge in that area? Charge in that area is A times sigma, right? So charge, so basically what is the importance of this charge densities is that if you know that charge density, you can calculate charge or of any other random arbitrary area. For length it is line, for volume it will be volume. Now what is the unit of this? Unit is Q by A, so its unit is coulomb per meter square. You need to remember this. So unit of surface charge density is coulomb per meter square. Now the last one is, as I said, volume charge density. Now we have moved one more dimension, that is 3 dimension. Let us consider a spherical surface. The easiest 3-dimensional thing is spherical surface. Okay, and if you consider this is charged, fully charged. Okay, it is charged in the volume, that means it is an insulator. Now if you are watching this video till now, tell me why this cannot be a conductor if I say this is a volume charge density. Okay, why this cannot be a conductor if this is a volume charge density. Now if you have to take a unit volume. Okay, unit volume, and whatever charge in that unit volume, that is called volume charge density rho. Okay, this is rho. It is spelled like this, rho. Okay, now any arbitrary volume if you consider, say volume V. Okay, if you say the volume is V, then what is the charge in that volume V? Charge in that volume V is volume times volume charge density, right? Charge in that volume is volume times charge density, right? So volume charge density is charge divided by volume. Now what is the unit of charge? Unit of charge is coulomb. What is the unit of volume? Volume's unit is meter cube. SI unit is meter cube. Otherwise there may be liter, there may be cc, but for SI unit it is meter cube. So this is the unit of volume charge density. Okay, so you need to remember these 3 things, but volume charge we will use not so much in this chapter. Maybe in future we will use, but line charge and surface charge density we are going to use. Let's look into them one by one. Before going into that, let us look into the Gauss's law. The statement of Gauss's law is electric flux through a closed surface is given by phi equals to Q by epsilon naught. I am going to explain it a little bit later. Now this flask is also, we have learned that flask is basically, what was flask? Flask is E dot ds, that is for a small portion. Now when we consider the entire surface, then this we have to do the integration, close integration. Okay, so for a small portion this is the electric flask, right, delta phi. Now when we consider the total flask, you have to remember that this is total flux through a surface. Okay, so for to calculate the total flask, basically phi is E dot ds, and that is equal to Q by epsilon naught. So Q is the total charge enclosed by that surface. What is the meaning of that? Let's look into that. So suppose we have a surface. Here this is a spherical surface. We are considering a spherical surface. Okay, and it is housing some charge Q. Okay, so this is a surface. Inside the surface we are considering a small charge Q. Now if you take a small area, okay, if you take a small area, and say this area, the area vector is delta S, and the electric field in this area, in this region, is E. Okay, then what is the flux coming out of this area? So flux coming out of this area, delta phi, is basically, obviously I told you, E dot delta S. Okay, now if you take this area very small, okay, that is delta S tends to 0, then we can write this as E dot ds, right? That is the differential. Now if we want to find the total flux, then that will be integration of E dot ds, right? Total is always integration. You have to remember these things, right? Now Gauss's law states that this total flux coming out of a surface is actually equals to the charge enclosed by the surface divided by free space permittivity. Okay, that is the Gauss's law. That is the statement of the Gauss's law. This part is not Gauss's law. Gauss's law is only this part on the right hand side. Okay, Gauss's law is only relating flask and charge enclosed. Okay, we are inserting this in between step so that it helps us to calculate electric field in some cases. That's it. Okay, there is E dot ds is not q naught by epsilon naught. That is not the Gauss's law always. Gauss's law basically says flask is equals to charge enclosed by free space permittivity, but we know that flask is E dot ds, so we are applying that and we are rewriting this equation. Now there are few very important points that you have to remember about Gauss's law. So what are those? Gauss's law is true for any closed surface, no matter what is the shape or the size. So we have discussed Gauss's law for a spherical surface. Okay, is it valid for if the surface is not spherical, it look like some odd surface? As long as the surface is closed, Gauss's law is valid. As long as the surface is closed, Gauss's law is valid. Okay, it does not matter on the shape and size. Okay, it can be like this, it can be cubical. Okay, does not matter, whatever is the shape and size, it will always be valid. Only thing you need to consider is it is a closed surface. Now why do we use this kind of surface? For example, why do we use spherical surface? Because for some symmetrical surface it is easy to apply the integration. That's it. Otherwise Gauss's law is not bound by the shape of the surface. So there are questions in the past that Gauss's law, is it applicable for a cube? Can we apply Gauss's law for a cylinder? Yes, we can apply, does not matter. Here this q, charge q, includes the sum of all the charges enclosed by the surface. The charges may be located anywhere inside the surface. So we know that phi is equals to q by epsilon naught, right? Suppose we have a surface. This q can be distributed anywhere, q1, q2, q3, q4. It does not necessary to be at the center. Okay, it is not necessary the charge is at the center, and it is not necessary that q is only single charge. It can be n number of charge and it can be distributed in the surface no matter how, but as long as the total charge q is basically sum of all the charges, Gauss's law is valid. Okay, it does not depend on the how the charges are distributed. Electric field is due to all the charges, but q is only for inside the surface. So let us understand this as well. So here we have the expression for electric field, right? So electric field E dot ds equals to q by epsilon naught. Now this q is only the q which is enclosed. Now we have the surface. We had 4 charges, q1, q2, q3, q4 inside the surface, right? So total q was, now suppose I have one more charge here, q5, one charge here, q6, another charge here, q7, another charge here, q8. Now if I have all these charges, if I want to find the electric field, suppose there is this Gaussian surface is not here right now, we want to find the electric field at this point. If I want to find the electric field at this point, then what will be the formula for that? Formula we already know that we have to apply the Coulomb's law, that is E is equals to E1 plus E2 plus E3 plus E4 plus E5 plus E6, that is sum of all the charges k q by r square, okay, qi by ri, I equals to 1 to 8 in this case. Okay, we have already learned that electric field due to multiple charges. Now this electric field inside this integration, is it due to only the 4 charges, or this is due to all the 8 charges? So this electric field is basically due to all the 8 charges, not only the 4 charges that is been inside the surface. Okay, that is what I was trying to explain, that this electric field is due to all the charges. Some charges may be inside, some charges may be outside, does not matter, but on our right hand side, this is only the charge inside the surface. Okay, this is a very typical concept that you have to remember. Some objective questions may come, practical questions may not come, where you have to do the calculations, but a conceptual question will definitely come. The surface that we choose for the application of Gauss's law is called Gaussian surface. So this surface that we have chosen to apply Gauss's law, this is called Gaussian surface. You have to remember this term, Gaussian surface. Okay. Next is Gauss's law is often useful to calculate the electric field for symmetric surface. I already mentioned that for symmetric surface, the surface is symmetric, then Gauss's law is easy to applicable. The most symmetric surface is the sphere, so we will try to keep our calculations involving spheres. In some cases we will apply for cylindrical surface, some cases we will apply parallelogram also, parallel pipe also. So whatever the symmetric surface, where there we will use the Gauss's law. Now let's look into a simple question. Okay, a cubical Gaussian surface has a side of length A equals to 10 centimeter. So cubical Gaussian surface A equals to 10 centimeter. Electric field lines are parallel to the x-axis. So electric field lines are parallel to the x-axis as shown. The magnitude of the electric fields through the surface ABCD and EFGH are 6 kilonewton per coulomb. So through this ABCD is 6 kilonewton per second, kilonewton per coulomb, and EFGH is 9 kilonewton per coulomb. Okay, so this is 9 kilonewton per coulomb. Okay, I am not writing the unit here. Okay, then the total charge enclosed by the cube. So they have asked you to find the total charge enclosed by the cube, and they have given you some option. Okay, so first we have to see what is given. So they have given the electric field lines. Okay, so E is given. Okay, and the side length is given. Now what we know, that what is the flux that is coming into the surface? What is the flux that is coming into the surface? So let's say flux in, it is coming in. Okay, remember the pipe example where water is flowing. Some water has to come in from one side and some water has to go out from the other side, right? So what is the flux coming in? Coming in is, we know that flux is given by E delta S. E dot delta S is the flux coming in. Now this is uniform electric field, right? So this is E1. E1 is 6. And what is the surface area? Surface area, this is a cube, right? So cubes, each surface has equal amount of area. What is the area? That is A square. A square is the surface area. Now this is 6 kilonewton. Remember that. Kilonewton means we have to convert it into Newton per coulomb. So we have to do 10 to the power of 3. Kilo means 10 to the power of 3. Now area is A square. A square means 10 centimeter. We have to convert it into meters. Remember, I told you, whenever you are converting into meters, always use 10 to the power of minus 2 factor. Okay, so 10 times 10 to the power of minus 2 whole square. Okay, 6 times 10 to the power of 3 times. So now what is this? You can simplify this here itself. Okay, 10 times 10 to the power of minus 2, that is, it will become 10 to the power of minus 1, right? 10 to the power of minus 1 whole square, that is 10 to the power of minus 2, right? So now simplify this, this will become 60. 60 is the flask coming in. Okay, I am not going into the unit, but I am just writing the value. Now similarly, can you tell me what is flux going out? 60 is coming in where it was 6 kilonewton. Okay, 60 is coming in when it was 6 kilonewton per coulomb. And what will be phi out if it was 9 kilonewton per coulomb? Obviously it will be 90, right? So coming in is 60, going out is 90. So what is the net flux? Net flux coming out, net flux is 90 minus 60. So that is the net flux coming out. So net flux coming out is 30. Now what you have to do? We have to apply Gauss's law. Net flux is given by, I am squeezing it here because after the class is over, this will be shared with you as a form of note, so that you don't miss out any steps that I am doing. So I am trying not to erase as much as possible. So phi sorry, net flux is given by Q enclosed by epsilon naught, right? So Q is basically, they have asked you to calculate the Q. So Q is net flux times epsilon naught. So net flux is 30. And I told you yesterday that what you have to remember for phi naught, epsilon naught, 9 times 10 to the power of minus 12. It is not 1 by 4 pi epsilon naught. It is only epsilon naught, right? So you have to remember the value 8.854, or you can remember it as 9 times 10 to the power of minus 12. So it will be 3 9s are 27. 1 0 we can cancel here, 10 to the power of minus 11. Now let's look into the answers. The answers in this question are given wrong. This is the same answer from the previous question. So if you see, the answer will be 27 times 10 to the power of minus 11. More precisely, it will be 0.27 times 10 to the power of minus 9. That you have to find. Okay, so or 0.27 nanocoulomb. If I remember correctly, you can check the question from 2023 question paper. It will be 0.27 nanometer. Okay, now let's move on. Now you have to remember formulas. We are not going into the derivation. Derivation will be covered in a separate series. I mentioned in between that you have to remember these formulas, because sometimes they might ask you numerical problems based on this simple formula. Okay, so now first thing is electric field due to a long straight uniformly charged wire. So line charge density, long wire, remember line charge density. So line charge density is lambda. If line charge density is lambda, then this can be written as the electric field for this charge distribution. E equals to 1 by 4 pi epsilon naught 2 lambda by r. Now in your book the value and the style given is something different. I ask you to remember this way because this helps you to remember that there is a 1 by 4 pi epsilon naught and 2 lambda by r. Okay, so 2 lambda by r. So basically if we are trying to find the electric field at any point, it has to be twice the charge density divided by distance. As you see here, electric field is proportional to 1 by r. Okay, that is also an important point that you have to remember. So for electric field to be proportional to 1 by r, it will be a single line charge density. Okay, for dipole it is 1 by r cube, for a point charge it is 1 by r square. Now again, another important thing, uniformly charged surface, a very long uniformly infinite plate. In fact, they have here it is infinite plate, but you don't see it is infinite. So basically this plate goes to infinity in all the direction, and one small piece is shown here. If you take this piece, and the electric field will come out to be E equals to sigma by 2 epsilon naught. So is there any r involved here? In the previous case it was 1 by r. In this case, no r involved. That means this is a constant. If the plate is infinite, then this value is constant. Now, most of the cases we do not see infinite plate, but for a finite plate as well, if this distance, when we are considering distance very close to the charged plate, this is still valid. So for charged object, charged plate, if we are measuring the electric field very close to the close to the plate, then it will be constant, almost constant. Okay. Now the last one, they have two parts. First part is electric field on the surface of a spherical shell. Shell means, what is the meaning of shell? Shell petrol pump? No. Shell is the cover. Okay, like egg shell. Okay, if you remove whatever inside the egg, and if you keep the white outer cover, hard cover as it is, then it is called a shell. Okay, or you can think of a plastic ball. Okay, you have to play, you played with plastic balls when you were a kid, right? So when the plastic ball is broken, you realize there is nothing inside, it is air only. So basically the outer cover, the hard cover, is called shell. Okay, shell has a strong outer layer but nothing inside. Inside it is empty. That is called a shell. Now here we are considering a spherical shell, so like a plastic ball itself. Okay, so now the radius of the shell is r, and if we charge it, if we give it some charge, where this charge will stay? This is a conducting shell, right? Even if it is not conducting shell, does not matter. Whenever you charge a shell, charges will be staying on the surface, or in case of if it is not a conductor, it will be very close to the surface. Okay, so almost you can ignore this width of the shell. Okay, so charge will be here only. If it is a conductor, it will only stay on the surface, so no problem. Even if it is not conductor, it is almost on the surface, so that is also okay. Okay, so charges are distributed on the shell. Now what you have to do, you have to calculate the electric field on the surface. When we are calculating the electric field at a distance r greater than the radius of the shell, okay, when the electric field is calculated at a distance r greater than the radius of the shell, in that case you can consider the entire charge on the shell is actually concentrated on the center. So entire charge, whatever charge is there, small q, that is concentrated on the center of the shell. Okay, and then you can calculate the electric field using this. So here, instead of small q, the charge is mentioned as capital Q. Now what is capital Q here? What is the capital Q here? If the charge density, surface charge density is sigma, it is given as sigma. Now what is the total charge Q? In that case, total charge Q 4 pi r square sigma, right? Surface area times charge density. This is how we can calculate the total charge. Okay, and any point inside the shell, it does not have any charge. Okay, it does not have any charge. If there is no charge, that means electric field is 0. So any point inside the shell, electric field is 0. Any point outside the shell, we can consider the entire charge is concentrated at the center, and we can calculate using simple electric field law. But when we are going inside, in this case, we cannot consider the charges to be at the center. Remember that. You cannot consider the charges to be at the center for points inside, because there is no charge. Only when we are going out, In that case, we can approximate all the charges as at the center. We can use simple electric field equation. Now, if you draw E versus R graph, okay, that is the electric field along y axis and the distance along r axis, then you will see this is the suppose this is the spherical shell. Okay, so here till this point electric field is 0. Till you are reaching R, electric field inside is 0, and from there it is decreasing with the value E proportional to 1 by R square. Okay, E proportional to 1 by R square. So for line charge density 1 by R, for surface infinitely charged surface it is constant sigma by 2 epsilon naught, and for a charged shell it is proportional to 1 by R square. Okay, I hope you have enjoyed today's lecture. Now time for today's homework. Homework questions will be given in the description below, and also it will be given in our website and WhatsApp channel. So I request you to join our WhatsApp channel and try to solve these two questions and mention the answer in the comment below. You can pause the video here if you want to. You don't have access to WhatsApp or website. You can pause the video. You can read the question. You can answer that question and mention that in the comment below. We have created a specific playlist for you where you can see all the videos that we are doing every day 9 p.m. We are going to upload one video, and that is available in our channel in our playlist. Playlist name is given here. Okay, this is the video 1 that we did yesterday. This is the introductory video available currently, and for everything I request you to join our WhatsApp channel if you want to stay updated about everything. Next is, if you liked our video, don't forget to subscribe to our YouTube channel, and I thank you for watching this video.